How you going? So we looked at the last video, we looked at kinematics and what it was all about. And it's good to be able to talk about what kinematics is, what each of the parts actually do, but to understand how it actually works, we have to actually do some examples. So we're going to look at a couple of examples today, and we're going to go through all the information so you can see what is involved, how we do it, and why we do things. So let's have a look at this question we have up on the board here. It says, a particle moves in a straight line with position relative to the origin, which is 0 here, given by the position vector of 2t cubed minus 9t squared plus 12t minus 5 centimeters, where t is equal to seconds and t is greater than or equal to 0. It wants us to find the expressions for the particles, velocity, acceleration, and then draw the diagrams of each. So let's get into that. We know that when it comes to kinematics, the position vector is our given s of t. The velocity function, so if we call this here a, v of t, remember, is equal to the first derivative of s of t. So in this case, if we differentiate this here, we'll get 6t squared minus 18t plus 24. Oh, plus 12, sorry. Plus 12. So this here is what my velocity function is. So we've worked out that the velocity function is the first derivative of this. However, it's asking us also to find the sign diagrams. So to find the sign diagram, we need to find the critical points. So we need to find out when does t, when do we have the factors that equate to 0. So in this case, we need to factorize this out. So I need to find out 2t, so I can factorize this here by 12. So therefore, if I do by 6, sorry, if I bring 6 out, I'll get 6 squared minus 3t plus 2 is equal to 0. And now I have an equation which I can actually equate to 0 and find the value of t. So therefore, this here just becomes a null factor law kind of question. Two numbers that multiply to give me 2, but add to give me negative 3. Well, because I've got a positive here and I've got a negative as the addition, I would assume that these here would be my numbers. Negative 2 times negative 1 is positive 2. Negative 2 plus negative 3 is negative 3. So, therefore, t has to be 2 or t is equal to 1. Now if we draw up the sign diagram for this, because remember these are our critical points, going back to the stationary points we looked at last time and our increasing decreasing, remember the sign diagram is a visual representation of what's happening to the graph around these critical points. So I have a critical point at 1 and I have a critical point at 2. Now I know that here t has to be greater than 0, so I'm going to put 0 here, so that means nothing can be less than that. And what I'm going to do is I want to plug in some values that are between 0 and 1 here to see what it actually becomes, between 0 and 1 and 2 here to see what it gets, and when it's greater than 2. So for instance, we might say, well, let's put 0.5 into the equation here. Now if we plug that back into this, 0.5 squared minus 18, 0.5 plus 12, we should in fact get a positive number. We should get a positive answer for that. So therefore, we can say that this part here is going to be positive. And because we're looking at linear kind of graphs here, then this here will interchange. So I have positive, negative, and then positive as my sign diagram. So that is the sign diagram for the velocity function. However, it's asking me now to find the acceleration. So a of t, remember, is just equal to the first derivative of v of t. So therefore, a of t is now equal to, if we differentiate this, we get 12t minus 18. And then it's just a matter of doing this kind of work again. So we want to equate this to 0. So therefore we have 12t minus 18 equals 0. let's see, whenever we get an opportunity to do it, we should factorise out. We could bring the 18 across and divide by 12, but factorising is always a good key to have if we do have that available. So if we bring out the 6, we'll get 2t minus 3 is equal to 0. So therefore, 2t minus 3 is equal to 0, 2t is equal to 3, and t is equal to 3/2. So we found our critical point here. So again, if we get our sign diagram out, and we call that A of t, we put in our critical point, so what's happening around this point? We chuck in a number that's going to be less than 3/2 and greater than 3/2. So we might say, well, let's plug in 1 here and plug 2. And if we do that, what you should find is you should get negative and positive, because what we're doing up here is, remember, we're doing this. 12 times 1 minus 18, which is the same as 12 minus 18, which is negative 6. And then over here, 12 times 2 minus 18 is equal to 24 minus 18, which is equal to positive 6. So I get a positive value. And this here is the sign diagram for my acceleration of this function. And that's part A done. Alrighty, let's look at part B. So part B is talking about the initial points. So, we know when something is initial, t is equal to 0. So, initial, t equals 0. So in this case, we want to work out what s of 0 is, we want to work out what v of 0 is, and what a of 0 equals. And if we plug those into each of these, if I replace all the t's with 0, I'm just going to be left with negative 5 centimetres. If I plug in the v of t, so remember v of t had, let's write this up here again, v of t was 6t squared minus 18t plus 12. If I plug that with a 0, I'm going to get 12 centimetres per second. And if I had a of t, that will be 12t minus 18. If I replace the t with 0, I'd get negative 18 metres per second. So this here is the initial. However, it's asking us to describe it. So we've got to talk about what is a particle actually doing at that point. And we would say that the particle is 5 centimetres to the left of the origin. It's a positive, so it's moving. So it's moving to the right at 12 centimetres per second. And we have a look at the signs. The signs are different and decreasing in speed. So what we've done here is, if we look at this in colour code, we'll call this here the red, we'll call this here the green, and then the black. The red part is this part. The green part is this part of the description, and the black part is this. So this is telling us where it is positioned, this is telling us how the particle is moving along, and this is telling me what speed it's actually travelling at. So we've described the initial conditions of that particle when t is equal to 0. Alright, so let's look at part C. Now, part C is asking us, well, find the times and position when the particle changes direction. Well, if we come back up to this here, we knew that t changes direction at 1 and 2, because we worked that out before. when we looked at finding the sign diagrams. Recall that those sign diagrams was V of t, where we had 1 and 2, so we have positive, negative, and positive. And A of t was, I think it was negative and then positive. So this was a sign diagram. So remember, this here is where it's changing direction, like it's a maximum and minimum. So we know that from part A, we already know the times when it changes. So we know that this changes at t equals 1 and t equals 2. However, the key to this question here is, well, what is it? What are its positions at that point? And we have the equation for the position. Remember, S of t is your position. So I just now need to plug these values into this equation to find out what the positions are at 1 second and at 2 seconds. So if I did this here, this then becomes 2 1 cubed minus 9 1 squared plus 12 times 1 minus 5, and that I think gives me 0. So after 1 second, the position is at its origin. We then look at 2, and again we just replace all the 1s with 2 in this one. So we'll get 2 cubed minus 9 2 squared plus 2 minus 5. And this here gives me negative 1. So we know that at 1 second, the particle's at its origin. After 2 seconds, it's to the left of the origin. So I've actually skipped C and gone to D. So this here is actually D. And the reason why I did this is because it's more closely related to what we've done here already. However, we also want to find the times when the positions were and the motion after 2 seconds. So what we do here is we know that if we look at C here, S of 2, V of 2, and A of 2. So I'm basically just plugging these values of 2 back into the 3 equations we worked out earlier. And what we should get here is we should get negative 1, 0, and 6 centimeters. So if we were going to describe this motion, we would say after 2 seconds, and we'll write this here, or not at 2 seconds, at t equals 2, we'll write at t equals 2, the particle is 1 to the left, or is to the left of the origin by 1 centimeter. It's not moving. So what we say it's at rest. So it's neither moving back and forth, so it's at rest. And because they're both positive and increasing in speed. So I'm looking at this here right now going, how can something increase in speed if it's at rest? Well, at rest basically means that, remember if we looked at a parabola here, if we threw a ball, remember at this point, this is where t equals 0, the v of t equals 0. At that instant point, the ball is actually not moving, it's just stopped, okay? But another thing that we can think about in terms of the velocity function here is this here is not just at rest, it's changing direction at that point. So at v of t is equal to 0, that's where it's changing direction. So it may be increasing in speed because it's actually moving from a positive to a negative, or left to right. And this here would be the description when it's at t equals 2 seconds. Okay, let's now look at, and we've looked at B and C and D, let's now draw the diagram. So if we were going to draw the diagram, I'm going to get rid of this here because that's in the way a second. Let's draw up our information here. Alright, I know that we had an initial point at -5. We have an origin. We had -1 up here. And we'll put 2 here. These are all our important points from everything that we have. Okay, I'm not worrying about the 3/2 because the 3/2 is going to help me out with this last question. That's all about acceleration. So we're just looking and drawing this diagram. So we now want to draw and illustrate the motion of this diagram. So if we think about this here is the particle. It's moving in a straight line, so it's just going back and forwards like this. When we draw a motion diagram, we have to actually be able to show how that movement's occurring. So what it looks like is we're doing something that kind of looks like this going above itself. But realistically, it's going over the top of itself. But we can't see that in a diagram. So we have to draw it as if we know what's happening as it's moving left or right. And that's why they look a little bit weird. So, initially, our particle was starting at -5. Because remember when we did that at the start, we said the position was at -5. We know that it turns at t equals -1 when it's at 0. So I'm going to put a point here. So I know that my particle is turning at this point. So it's going from right, changing back. And it changes again after 2 seconds at -1. So I will then come back here and move. So this here would be when t is equal to 0. This is when t is equal to 1. And this is when t is equal to 2. So in terms of time here, at the initial point, the particle was 5 centimeters away from, to the left of the origin. After 1 second, it's back at the origin and turning, changing direction. After 2 seconds, it's now at -1 centimeters away from, it's 1 centimeters to the left of the origin, and it's turning again, and then it starts moving towards the right. Okay? So this here is the motion diagram of what we've calculated all the way up until part E. So our initial point, where it changes direction, because we worked out that this happens from going positive. So look at this, how it works here. We're going positive, then we go negative, so we're going back to negative. And then we go positive again when t equals 2. Okay? So this here should line up with what these are doing in this case. Positive, negative, positive. So positive, coming backwards, negative, and then positive again to the right. So this here is the motion diagram that represents this particle that's moving in space. Okay, what about part F? Well, part F is determine the time intervals where the particle's speed is increasing. And that's where this is really important. Because remember, we know when a particle's particle is increasing is when the velocity function and the acceleration function have the same sign. So, where do they have the same sign in here? We can see here that it's negative, and we know this here is going to be 0. It's negative between 0 and 1.5. When is it negative up here? Well, it's negative between 1 and 2. So therefore it has the same sign between 1 and 3/2. So between 1 is less than equal to t and less than equal to 3/2. That is when it has the same sign. So that's when it's increasing in speed. So between 1 and 1.5, it's increasing in speed. So, okay. And another time, where else is it increasing in speed? Well, could we say when it's greater than 3/2? Because it's positive there, and it's positive 2 as well. We could, but we would be wrong. Remember, between 1 and 2, that's negative. It's only positive for the acceleration when it's greater than 1.5. So therefore, between 1.5 and 2 for up here, that's negative. So therefore, it's not the same sign. It only becomes positive when they're both greater than 2. So therefore, another time that it's increasing in speed is when t is greater than 2. So this is kinematics, the study of motion using derivatives. Can be very, very confusing, but you just need to be able to match up those specific words with what you're doing with these questions. Lots of work. It is always a large question, this one. And therefore, it's really important that if you're struggling with the idea of sign diagrams, you're probably going to struggle a little bit with how this works. Because remember, as we looked at this before, this here is telling us how this is telling us. This is what the graph looks like. It's telling us it's positive, and then suddenly it goes negative, and then it goes positive again. Okay? We know that we can only find this by finding the first derivative of s of t. And we can find the acceleration by finding the first derivative of v of t. Very confusing, but it is manageable. We'll have a look at another example in our next video, and hopefully it's making more sense to you.